In last class, I have discussed about the various aspects of design of retaining walls, and then different types of retaining wall, that is gravity retaining wall, semi gravity retaining wall, then cantilever retaining wall, then counterfort retaining wall. Now, in this class, I will basically solve one example on cantilever retaining wall to show that how the dimension of this retaining wall is decided, and what are the factor of safety or the safety that we have to check and during the design of this retaining wall. Now, first if I go for the problem. Now, suppose if we take one retaining structure which is a cantilever retaining wall in this form. Suppose this is the retaining wall and ground surface is this one. Now, this ground surface or the backfill side, which is making an angle I equal to 15 degree with horizontal, and this is backfill side, and this one is the existing ground surface. Now, this first for the first trial based on the guidelines that I have given in the last class, I have chosen this dimension of this retaining wall, that for this top portion I have taken this is 0.3 meter. Then and this height of this retaining wall from this here to here, that height is 4.8 meter, and this thickness that I have taken, thickness of this base slab is 0.6 meter. 0.6 meter. So, below this ground level, the total distance below this ground level is 1 meter basically to the base of the slab. Now, what are the other dimensions that is taken, like if we extend this, because this triangular portion. So, the dimension of this portion, as I have mentioned, that this distance from here to here is taken as 0.6 meter, that means from here to here. This is the toe. Then this distance, if I extend this triangular part, so this distance is taken 0.2 meter. Now, as usual, as I have mentioned that top portion is 0.3 meter. So, this one is also 0.3 meter, and this total slab distance or length is taken as 3 meter. So, the total base width of this retaining wall or base distance is 3 plus 0.6 plus 0.2 plus 0.3, that is 4.1 meter. So, that is basically 0.3 plus 0.6 plus 0.2 plus 0.3, which is equal to 4.1 meter. Now, the other distance or this things we can take the extend these vertical lines, which is passing through this edge of this retaining wall. Then we divide this total retaining wall, as we will solve this problem, particular this problem by using this Rankine's theory, that we will solve this problem by using Rankine's theory. So, as I have mentioned that we will consider the weight of this soil also. So, first we consider that our active earth pressure which will act at an angle of 15 degree with horizontal, and the point of application that will act at a distance of this total vertical line to the 1/3. Now, the distance of this total vertical line, before we start, we can determine the distance of this portion. So, this portion is tan 15 into 3. So, distance from this point to this point is 0.8 meter, that is will come from tan 15 into 3. So, the total height of this vertical line from say A to B. So, distance A B, that will give us the distance or this height is 0.8 for this one, then 4.8 for from here to here, then additional 0.6 meter the thickness of base slab. So, total the distance that is height is 6.2 meter. So, the point of application of this lateral earth pressure is 6.2 divided by 3, which is 2.07 meter from the base of the retaining wall. Now, as from this design you are neglect the effect of this passive resistance, but for this can also be included in the calculation, but for the first case this problem will be solved by neglecting this passive pressure. So, now if I want to solve this problem by Rankine's theory, so as you have to check whether Rankine's theory can be applicable or not. So, if I determine this angle, so this angle we can determine the expression is 45 degree plus I by 2 minus phi dash by 2 minus sin inverse sin I divided by sin phi dash. So, now the values which is given for this problem, that phi dash is 32 degree, delta is 23 degree, delta is the friction angle between this concrete retaining wall and the soil. And here for the simplicity, that it is assumed that this is the foundation soil, this is backfill and this is a foundation soil, and assume the properties are same for both the soils, foundation soil and backfill soil. But if some cases this property may not be same. So, in that case we have to consider different properties for different conditions. So, for the foundation soil calculation we have to then the delta of the base of the retaining wall and the soil, that friction angle will be based on the foundation soil properties, and this friction angle delta which is with backfill and the retaining wall, that will also change, and that will depend on the backfill properties, soil properties. So, then in that case the delta of these two may not be same. So, that consideration you have to taken care into our calculation if the soil properties are different for the foundation soil and backfill soil. But for this problem we consider both the properties are same for this soil total system. So, now the delta for all the system is 23 degree, the unit weight is 19 kilonewton per meter cube, I which is 15 degree, and the allowable bearing pressure is 400 kilonewton per meter square. So, now we have to solve this. Another, the unit weight of concrete is taken 24 kilonewton meter cube, and unit weight of soil is taken as 19 kilonewton per meter cube. So, first we have to determine this angle, so that we can check whether this value is Rankine theory can be applicable or not. So, this angle we can determine by 45 degree plus 15 degree by 2 minus 32 degree by 2 minus sin inverse sin 15 degree divided by sin 32 degree. So, this value is coming out to be 7.26 degree. So, if this value is 7.26 degrees, so this line will pass through the backfill soil, it will not pass through the vertical stem of the retaining wall. So, as this angle is very small. So, we can consider that the Rankine's theory can be applied. So, this is the first check we have done, that there we can use the Rankine theory. Now, we will proceed for the other sections. Now, first we will calculate what is the active earth pressure that will act into this soil or into this retaining wall. So, first we will calculate this P A, that is equal to half into K A into gamma of soil into H square. Now, H we are taking this, as I mentioned, that H we are now taking the total vertical distance from A to B, the total height we are taking, and that A B is 6.2 meter. So, if I take this 6.2 meter, then K A by using Rankine's theory, if we can consider this K A is cos I into cos I minus root over cos I square minus cos phi dash square divided by cos I plus root over cos I square minus cos phi dash square. So, if I put this value, so then this is cos 15 degree into cos 15 degree minus root over cos 15 degree square minus cos 32 degree square divided by cos 15 degree plus root over cos 15 degree square minus cos 32 degree square. So, this K A value, if I solve this thing, this K A's value is coming 0.34. So, this is 0.34. So, the P A value is equal to half into 0.34 into gamma is 19 into H is 6.2 square. So, this value is coming 124.2 kilonewton per meter, as we are calculating this thing per meter distance. So, this is per meter. Now, as from this figure we can see that P is acting as an angle of 15 degree. So, we can take the vertical components and horizontal components of this P A, that we can write like this is P V and this is P H. So, this is the vertical component of P A, P V, and P H is the horizontal component of P A. So, we can calculate that P V is P A into sin 15 degree, that is equal to 32.15 kilonewton per meter. Similarly, pH is Pa into cos 15 degree, which is equal to 120 kilonewton per meter. So, the vertical force and horizontal force that is coming due to the lateral earth pressure of the backfill that we have calculated. Now, we have to calculate the other parts of this problem. So, now for the other parts, suppose if I take the previous figure, our main figure, then in this total retaining wall, we can take several parts of the retaining wall. So, we can take this is number 1. This number 1 means this rectangular is our first component. Then this triangle is number 2, that means this triangular zone is number 2. Then this total base slab is third zone, and this total rectangular soil portion is fourth zone, and this triangular soil portion is zone 5. Now, we have to determine the individual weight of these 5 zones, their centroid where these weights are acting actually, and then the moment with respect to toe. So, all these things we have to calculate, because these 5 zones, this load are giving the vertical force, and that will also give the resistive moment, and this P A, due to this P A will get the overturning moment. So, first we have to calculate the weight of different portion of this total system. Now, first if we calculate this weight, we can take for the weight calculation, we can take this table, we can make this table, that is our serial number. Then weight calculation, that is kilonewton per meter. Then the force that we will calculate, that is also kilonewton per meter, and this force can be vertical and this can be horizontal. So, this is for the weight calculation table that we will calculate the first serial number 1, the first segment weight that we will calculate. So, for this first segment, this is for the first segment, the weight will be this area into the unit weight of the concrete. So, this area will be 4.8 meter into 0.3 into 24. So, if in this way, if we calculate the weight of every section, then weight 1 for the first section is 0.3 into 4.8 into 24, that is the unit weight of the concrete. So, and this will act in the vertical direction. So, in vertical direction we can write the total weight W 1, that is equal to 34.56 kilonewton per meter. Similarly, if we calculate the weight of second portion, that is a triangle. So, that we can write half into 0.2 into 4.8 height and then 24. So, we will get this value is 11.52, and this will also act in the vertical direction. So, we will get this is also 11.52. Similarly, the third weight, if we calculate the weight of the third segment. So, that is 0.6 into 4.1 into 24, because for the third segment means this total base slab. So, that is 4.1 into 0.6 into 24. 0.6 is this distance and 4.1 is total base slab width, and then for 24 is the unit weight of the concrete. So, if I use this value, then it is come 59.04. Then for the fourth section, that is for the soil, fourth and fifth portion, that is the fourth and fifth portion, fourth this rectangular portion and fifth this triangular portion, this is for the weight of the soil. So, for the fourth portion we can write this is 3 into 4.8 into 19, as the unit weight of this soil is 19, and for the triangular section it will be half into 0.8 into 3 into 19. So, in that way, if I write fourth section, that is 3 into 4.8 into 19. So, vertical force, again this soil pressure will act in vertical direction, the 273.6. Now, for the fifth segment, for the triangular one for the soil, that is equal to half into 0.8 into 3 into 19. So, that value is 22.8 kilonewton per meter. So, these are the vertical loads, vertical force that is acting due to the concrete and the soil. Now, we can write the next two forces, that is the horizontal and vertical forces acting due to the lateral earth pressure. So, sixth segment we can write this is P v, that will also act in vertical direction. So, that P v value is 32.15. Then the seventh one is P h, horizontal force. So, that means P h will act in horizontal direction. So, that is 120 kilonewton per meter. So, so we can write the total vertical force summation of V, that is equal to the summation of this vertical column is 433.67. Similarly, summation of this horizontal force total 102 kilonewton per meter. So, summation of total vertical force is 433.67 kilonewton per meter, and summation of horizontal force is 120 kilonewton per meter. So, this is force table. Now, we will calculate the moment table. So, once we calculate the moment table, so this table will calculate. So, this is the force table, the next one is the moment table. So, again this is also serial number. Then we will consider the vertical and horizontal force, that is force. So, now we can write the next column is, this is serial number. We can write the next column is our lever arm with respect to toe. The next one is the moment. Now, this moment can be over resistive moment M r, and this can be overturning moment M o. This is kilonewton per meter per meter. So, first we will go for again this 7 force that we have taken, first, second, third, fourth, fifth, sixth, seventh. So, from the force table we can write the value of these forces. So, for the force table, first vertical force for the first segment is 34.56, then second one is 11.52, then third one is 59.04, then fourth one is 273.6, fifth one is 22.8, then the sixth one is 32.15, and seventh one is 120, which is horizontal. Now, for the each segment we have to calculate the lever arm. So, now if I consider the first segment, this is the first segment. So, it is a rectangle. So, this will act the center of this rectangle. So, lever arm from the toe will be 0.6 plus 0.2 plus 0.3 divided by 2. So, that as it will act the center of this rectangle. So, that is 0.6, 0.2, 0.6 plus 0.2 plus 0.3 divided by 2. So, now if I write in this form, so the lever arm will be for this first segment is 0.6 plus 0.3, sorry 0.2 plus 0.3 divided by 2. So, this will give us the value 0.95. Similarly, for the second one, second is a triangle. So, second segment is a triangle. So, here lever arm will be 0.6 plus 2/3 of 0.2. So, that will give you the lever arm of the second triangle portion. So, for the second portion, the lever arm is 0.6 plus 2/3 of 0.2. So, that will give 0.73. Similarly, for the third section, that is the base of this rectangle. So, that will give us the straightforward, this will act the center of this rectangle. So, 4.1 divided by 2. So, lever arm for this third portion is 4.1 divided by 2, that is equal to 2.05. Now, lever arm similarly for the fourth section, that is the rectangle of this backfill soil. So, that is 0.6 plus 0.2 plus 0.3 plus 3 divided by 2, that is equal to. So, that means here this is 0.6, 0.2 plus 0.2 plus 0.3 plus it will act the center of this 3. So, plus 3 by 2. So, now this lever arm is 2.6. Similarly, for the fifth segment, that is for the triangular zone. So, that lever arm is 0.6 plus 0.2 plus 0.3, then it is a triangle. So, triangle means plus 2/3 of 3. So, it will give 3.1. So, these are the lever arm value 0.951, 0.73, 2.05, then 2.6, then 3.1, and for the sixth one, that is acting vertically at a distance of 4.1 meter. So, that is 4.1 meter for the sixth one, and as we have calculated that the horizontal one, that is the vertical one, will act 4.1 meter from the toe, and the horizontal will act 2.07 meter from the toe. So, that distance is 2.07. So, these are the all rounded values are the lever. Now, from these vertical forces corresponding to that moment will give the resistive moment, and the moment corresponding to this horizontal force, that will give the overturning moment. Now, if I calculate this moment, so this is simply 34.56 into 0.95. So, this will give resistive moment is 32.83. So, this is actually 34.56 into 0.95. So, that give you 32.80. Similarly, for the second one is 11.52 into 0.73. So, that value is 8.41. Similarly, for the third one is 59.04 into 2.05. So, this will give 121. The fourth one is 273.6 into 2.6, that is given 711.36. The fifth one is 22.8 into 3.1. So, this will give 70.68. Sixth one is 32.15 into 4.1. So, this will give 131.8. And the seventh one is 120 into 2.07. So, that will give 248.4. So, these are the resistive moments and the overturning moments. Now, if I take the summation of all these moments, so that means summation of m r, that is equal to summation of this column is 1076.1 and summation of overturning moment is 248.4. So, we can write that m r is 1076.1 kilonewton meter per meter, and m o is 248.4 kilonewton meter per meter. Now, we have completed the force table, done the moment table, then we will calculate the, or we will check the factor of safety for different condition. The first factor of safety that we will check, that is for the sliding. So, factor of safety for sliding and that is the expression is total vertical force into tan delta divided by all horizontal force. Now, here total vertical force summation is 433.67 and tan delta that we have taken is 23 degree. So, into tan 23 degree and summation of all vertical horizontal force is 120. So, this value is equal to 1.53, which is greater than 1.5. So, that means it is safe. So, now next check that we will do for the overturning moment, factor of safety for the overturning. And that is summation of resistive moment divided by summation of overturning moment. So, summation of all resistive moment is 1076.1 divided by 248.4. So, that will give us 4.33, which is greater than 1.5. So, that means it is safe. The first two check we have done and it is safe against this sliding and the overturning. Next, we will calculate the E value or the no tension condition. So, first we calculate the x bar, that expression I have given, that x bar is summation of m r minus summation of m o divided by summation of all vertical force. So, summation of m r is 1076.1, m o is 248.4 divided by vertical force is 433.67. So, it is coming 1.9 meter. So, E we can eccentricity we can calculate, it is the B divided by 2 minus x bar. B is the total base width, and here total base is 4.1 divided by 2 minus 1.9. So, it is coming 0.15 meter. So, and definitely which is less than B by 6. So, this no tension condition will occur. So, this is fine. So, next check we will calculate for the bearing capacity calculation. We have done the 3 checks, that is the sliding, overturning and the no tension condition. Now, for the bearing, calculate first P max, and that expression is all vertical force divided by base width 1 plus 6 E divided by total base width. Now, for vertical force is 433.67 divided by base width is 4.1 into 1 plus 6 into E is 0.15 and divided by 4.1. So, this P max value is 129 kilonewton per meter square. So, now factor of safety for the bearing is the allowable force, that is 400 kilonewton per meter square divided by this allowable bearing pressure is 400 kilonewton per meter square divided by 129. So, that value is 3.1, which is greater than 3. So, safe. So, in this way we have checked all the factor of safeties, that is for the sliding, overturning, then for the no tension condition and a factor of safety for the bearing. So, all the checks are satisfied. So, the dimension that we have chosen, that is okay for all the condition, here it has satisfied all the factor of safety. So, we can use this dimension for our purpose. Now, there are few things that we have to mention, that suppose this problem is partially unsafe or slightly unsafe by the sliding. In that case, one thing we can do, that if this problem is not satisfied, suppose this is our retaining wall structure, so this is the retaining wall structure, ground surface, this is ground surface. Now, say this retaining wall is unsafe against the sliding, then one thing we can do, that we can provide one key here, this in this form, just to increase this another portion that we can extend, which is called key. The idea of this key, this will give the additional resistance against the sliding. So, and another thing is that when you calculate the passive resistance, that passive resistance part, that depth will also increase, because here we will calculate the passive resistance, say P p. So, that passive resistance depth, that will also increase. But one thing for the factor of safety, so this will increase the passive resistance for this design, which we have although have not considered in our previous calculation, but this passive resistance we can increase, and this will give the additional resistance against the sliding. So, if it is marginally unsafe against sliding, we can provide keys. Now, when we can provide key, one thing for this situation, that the properties for the soil, for this portion, say phi 2 is the base property, soil property, and C 2 is the foundation soil property, and say phi 1 is the backfill soil property, C 1 is the backfill soil cohesion, this is friction, this is the foundation soil. Now, instead of taking the full in the situation when key is used, instead of taking full phi 2 and C 2, generally it is reduced by half to 2/3 of the value of for the extra safety. As for the pool passive resistance, because in this case as this key we are applying for this portion only. So, it is doubtful that whether the full passive resistance will be developed or not. So, that just to the for additional factor safety, this soil property C n phi is reduced by half to 2/3 for the additional factor of safety. So, now this is the function of key. Now, another thing is that if we solve this problem, that we have solved this problem and where this the soil properties are same for both the cases. And another one, that when we are talking about this theory, that we have used the Rankine's theory. Okay. Now, we can solve this problem for Coulomb's theory also. Now, this is the home assignment for you. If you want to, you can try to solve this problem by Coulomb's theory, by applying the Coulomb's theory, and you can see the what is the difference we are getting by if you use the two different theory. Another one, that we are neglecting this passive resistance. Now, if we can solve this problem by using this passive resistance, that also you can try to solve this one with use of passive resistance. We can see how much extra factor safety you will get when you consider this passive resistance. That these two things, by considering passive resistance and using a different theory, we can try you can try to solve this problem, same problem. Now, when you talking about the retaining wall, the next segment that when talking about the retaining wall, it is most of the cases is this the backfill material which is used mostly which is used for the granular soil to avoid the water pressure, because when you design the retaining wall, you always try to avoid the induce of water pressure. So, that this additional water pressure will not come into retaining wall. So, that to avoid this water pressure, there are few things we can do, that we can provide some holes in the retaining wall. So, that water can pass through that hole. So, that the water pressure can be neglected. Suppose if this is one retaining wall structure, that suppose this is one retaining wall structure, this is base, this is the ground surface. So, we can provide a hole or a water body can pass through this portion. This is called weep holes, W P weep holes. So, we can provide some filter material, we can provide some filter material here in the weep hole. So, suppose this is backfill material. So, this is filter material. Now, this filter material, this weep holes, this diameter is around 0.1 meter, spacing is around 1.5 meter to 3 meter in horizontal direction. So, now this use of these weep holes is to reduce the pore water pressure developed due to the water. Now, this pore water pressure, if we can reduce this, so if all the water can pass to this weep holes, then we can reduce the pore water pressure. So, that pore water, so that the additional lateral earth pressure that we can reduce by this way. Now, another one that we can consider these different types of weep holes, that this is suppose a retaining wall. We can provide a perforated pipe here with filter material surrounding this. So, that water can collect here and it can pass through from the retaining structure. So, that is our perforated pipe. And this is filter material. Now, if this is for the granular soil or sandy soil, now for the clay soil, when fine grained soil is used, because we always try to use, this is for the sandy soil or granular soil. Now, case 2, if for the clay soil or fine grained soil, we always we always try to avoid the use of this fine grained soil, but sometimes if it is not possible to avoid this fine grained soil, then what we can do, suppose this is our retaining structure. This is existing ground, this is the ground surface. Then we can provide a filter material along the vertical surface, or we can provide, and then we can provide a path, so that water can collect here and it can pass through. So, this is weave hole. So, this is our filter material or vertical filter. Now, this filter material can be inclined also. Suppose this is the retaining wall. So, that material can be inclined, and then we can provide the weave holes here. So, this vertical material can be, this is inclined material, filter material. So, in this way we can reduce the water pressure. This is for the fine grained soil, the inclined or vertical filter, then the water can be collected through this filter and can be passed through these weave holes, or this is for the sandy material, where we can provide the weave holes or we can provide the filter materials. Now, for this, so this can be done for the retaining wall design. Now, when we are talking about the retaining wall design, so this the design of counterfort retaining wall. That this counterfort, this basic difference of counterfort retaining wall, that in case of reinforced, suppose if this is the retaining wall, that counterfort retaining wall, this is the retaining wall counterfort portion. So, when you determine the dimension of this front portion, this retaining wall, or this is similar to the cantilever retaining wall. So, in based on that, the same as we have discussed for the cantilever retaining wall design procedure, we can determine the this dimension of this counterfort retaining wall also. But in case of reinforcement design, that is the difference between the retaining wall for the counterfort and the cantilever, that for the counterfort retaining wall, that counterforts are placed with certain spacing, say point. So, this counterfort are about this 0.3 meter thick. So, suppose this is 0.3 meter thick, and spacing between these counterforts is taken at 0.3 h to 0.7 h. And when you taking the reinforcement design, because when we are designing this retaining wall, then this you have to design for this base slab. So, this idea of the use of this counterfort as a spacing, a certain spacing, to reduce the induced bending moment and shear force in the base slab as well as in the cantilever portion, this cantilever slab. So, that will we have to design when you consider this, when you design the reinforcement part. But for the dimension part, that is the main aim of this class. So, that dimension you have to decide based on the similar as we have discussed for the cantilever retaining part. Now, another case, suppose we want to, that is for the counterfort and the cantilever retaining wall. Now, for the gravity retaining wall, suppose if we want to this gravity retaining wall, so this is our ground surface, this is the base. So, here we can solve this example in two methods, as we have solved is for the cantilever retaining wall also. Here the process is, we can solve, if we want to solve it by Rankine's method, then you have to extend this part, then it will act at a horizontal angle I, and then you have to consider the weight, and you have to suppose if it is this form, then we divide this part. Suppose this is segment 1, segment 2, segment 3, segment 4, segment 5, segment 6. The same process we have to follow when you choose the dimension. We have to first choose the dimension based on the guideline that I have given. Then you have to calculate the weight of individual section, that is first, second, third, fourth, fifth, sixth. So, this is for the weight of the soil, this portion, and then before that you have to check again whether the Rankine theory can be applied or not. So, then you calculate, if it is applied Rankine theory, then you calculate the weight of these concrete blocks, 4 section, and weight of the soil. Then with respect to toe, we have to take the moment, as we are neglecting the passive force here also. If you want, we can consider the passive force in the calculation. Now, we take the moment as I have solved for the cantilever retaining wall, then check all the factor of safety. So, that is for the gravity retaining wall, same we can consider. Now, if I consider the same problem by Coulomb's theory, then suppose this is I. So, it will act with this perpendicular line with an angle delta, this P A will act. So, again we can take the different segments, this is say 1, 2, 3, 4. But here we will take the weight of this 4th section, only these concrete blocks, and then we will not consider the weight of this soil for this analysis. Then the process is same, we will consider the, we will take the moment of this all the forces with respect to 2, and then you have to check the all the condition, that is for our sliding, then overturning, then no tension condition, then bearing. So, these are the design procedure that we have mentioned for this class, that how this retaining wall, that basically the dimension of the retaining wall can be chosen for different condition, and the basic difference of, and then what are the difference of different types of retaining structure, that is for our gravity, semi gravity, cantilever and counterfort retaining wall. And in the design aspect, the difference in the cantilever retaining wall and the counterfort retaining wall, that when we are considering the reinforcement design, for there the counterforts are used. So, we have to redo there is counterforts we have to design. So, those things, but the dimension consideration, the dimension of this counterfort retaining wall, that approach is similar to the cantilever retaining wall. So, now and we have discussed about how to reduce the water pressure in the retaining wall by providing the weave holes. Then we have discussed that if there is this retaining wall is slightly unsafe against sliding, then by providing key we can increase the sliding bearing capacity, and then that the passive resistance that is giving, that passive resistance will increase. But when we use the keys, we have to keep in mind that the full development of passive resistance, that is whether it will develop fully or not, that is a question. So, that it is better for the safety purpose if we reduce the soil properties C of I by 2/2 to 2/3 to its original value. So, that we can reduce this value, because we do not know whether this resistance will fully occurred or not. So, these are the things we have to keep in mind when we consider design the retaining structure. So, next class I will discuss about the various other aspect or various other types of retaining structure in the geotechnical engineering, and then we will discuss about the how to choose the depth, because in this there is another type of retaining structure, or that is our sheet pile. So, what is sheet pile, then what is the difference between the sheet piles and the cantilever retaining structure, because sheet pile is also one type of retaining structure, and then how to differentiate between these two, those things we will discuss in the next class. And then I will try to solve what are the different types of sheet pile, and then how to solve the to choose the dimension of those sheet piles, that things we will discuss in the next class. Thank you.